All right, welcome back again, everybody. Today we're going to be doing section 11.7. This is a super duper short section. This is just about a strategy for testing series. So at this point, we've pretty much gotten all of the tests that we're going to learn to determine if a series converges or not. And now we're just going to play. So I have some basic strategy guidelines. So I'll just get started. Here we go. The first thing I've got to say outright is that when you're determining the convergence or divergence of a series, it really is kind of an art, and there are no hard and fast rules for doing so. This is one of those points in mathematics where everyone, or I shouldn't say everyone, people are just kind of split. Some students really, really like this type of mathematics, and some students really, really do not like this type of mathematics. So don't feel bad either way. They're normal responses, but there's no hard and fast rule. There's no simple procedure that says do this, do this, do that, and you'll get to the end. You really do have to kind of like get your hands dirty and dig in and massage the kinks out of things and pull things apart and look at the pieces. That's really what it takes. It's kind of like with integration, right? It's really just a skill that's learned through practice and through pattern recognition. You want to be able to recognize patterns and so on. Um, Basic tip right off the bat, it's unwise to just try the tests in some random order. It's unwise to be like, oh, just alternating series test or ratio test or root test or that's not a good method for not a good strategy for determining if a series converges or not. However, I do have the following 8 tips and guidelines that can help a little bit. That can help a little bit. So here's the first one. Given some series, if you can tell at a glance that the limit of the terms is not 0, then try the divergence test. And I have this note here. This test often gets lost in the shuffle because there's just so many tests. There's so many tests that we have, and it's really easy to just forget the test for divergence. Literally, to look at look at this sequence in here and see if it goes to 0, right? If it doesn't go to 0, then your series doesn't converge. So that's it, right? So if you can tell that this thing doesn't go to 0, try the divergence test. The other thing is if your series is of one of these two forms, then maybe the p-test would be helpful, or the alternating p-test. So remember, the alternating p-test is one that we got during activity, right? So you're allowed to use that test. There's the p-test and there's the alternating p-test. So if you've got something that looks like a p-series, maybe try the p-test. That's a good tip. If your series has this basic structure, meaning if it kind of looks like a geometric series or if it can be massaged into the structure of a geometric series, then use the results about geometric series that we got back in section 11.2 or 11.3, right? So if you can get it into that form, then you can use those results. If a series has a form that's similar to a p-series or similar to a geometric series, but not exactly that type, then the direct comparison test or the limit comparison tests should be considered. And I feel like this is where the most artistry is involved because you're really just trying to get bounds on things. You're trying to get an inequality set up that lets you determine if something is bigger than or smaller than something else. So this is where I have a lot of fun, honestly, just trying to get an inequality to hold that lets me bound something. Direct comparison or limit comparison tests. A little tip for the LCT. I know I've mentioned this in activity as well, but if your summand is a ratio, try to compare the series with the series that would result if you divided the highest power of the numerator by the highest power of the denominator. So let me explain that a little more clearly. A lot of times when you're trying to use the limit comparison test, the very first question you have is, what do I compare it to? And a good tip for using the LCTs to, well, how do I say this? Basically, if you've got something that looks like this, then you may want to compare it to a series that results when you divide the highest powers. That's really what I mean. So this is asymptotically equivalent to 1 over n. That's really what I mean in a more precise way. This is asymptotically equivalent to 1 over n. So maybe try comparing with the series sigma 1 over n. And that is usually a good rule to help the limit comparison test work out. And if you actually go back and look at the examples from the lecture and the slides in section 11.5, or I'm sorry, 11.4, where we got those tests, you'll notice that those were always the series that I compared to. I basically was like, oh, well, this thing is basically asymptotic to 1 over n. Let's compare to the series 1 over n. So that's a good tip for the LCT. If your series is alternating, try the alternating series test. um, that's an obvious possibility. If there's an alternating factor going on, something like this, or this, that's a tell for those who play poker. That's a tell that you've got an alternating series, so maybe the alternating series test will help. Right. This one's about the ratio test, and this one I talked about in the last lecture already. Series that include factorials or other products can often be dealt with using the ratio test, but the ratio test is not very effective if there are a lot of terms in the summand. The reason for that is when you go through the calculations of the ratio test, you're really looking for multiplicative cancellations. You want a factor in the numerator that is equal to a factor in the denominator, and you want to cancel those factors. But if you've got a whole bunch of sums inside your sum and, then you're not going to have multiplicative factors. You would have to actually factor the numerator and the denominator and then cross your fingers that something would cancel. So for example, series that have stuff like natural log, sine, cosine, tangent, they don't yield well to the ratio test because you always end up with expressions that look like these. And those expressions are unwieldy, and you're not going to be able to cancel, for example, tangent n with tangent n plus 1. You're not going to be able to make that cancellation. They require gnarly identities to simplify. So you might have all of the angle sum formulas memorized, and you're welcome to apply those after applying the ratio test, and you might get lucky. You might get lucky that you'll have a nice cancellation. But generally speaking, um, try to avoid using the ratio test when you see stuff that's got this in it. That's my tip. When you're faced with these types of expressions instead, if you've got natural logs, sines, cosines, tangents, I recommend the direct comparison test because it's really what it boils down to. Some kind of direct comparison where you know a series converges or diverges and you can compare your series to that series, and then you can tell if it converges or not. So if you got those types of things, direct comparison, limit comparison, or use the integral test as a last resort. The integral test can be nice for things like this, as long as as long as the integral is easy to evaluate, right? If the integral is gross, if the integral is not going to just easily be evaluated, may not want to use the integral test. All right. Um, Also, naturally, a series for which the summand is wrapped in an exponent, those suggest you should use the root test, like we talked about earlier. The root test can also be used on, quote, geometric looking series. So if you've got a series that kind of looks like a geometric series, sometimes the root test can be easier than just trying to make things become a geometric series. Here's a good example. Here's a good example right here. This is geometric looking in that it's kind of like something to the power n. Well, try the root test. Try the root test. Take the nth root of this and then see where, or the nth root of, oh yeah, the nth root of this and then see what the limit is as n goes to infinity. That's the idea. All right. And then last little tip here, if your sequence, your summand, looks like, if your sequence that you're adding up looks like something that would be easy to integrate if it were a continuous variable function, then maybe try to use the integral test. That's all I can say about the integral test. The integral test is basically good when the thing looks like an integral that would be easy to evaluate. That's when the integral test is usable or easy to use, I should say. All right. So I won't dwell too much longer on it. On that note, let's play. This activity is literally just practicing determining the convergence of a whole bunch of series. And I will say very directly that that is going to be what the test is. The test will basically be a handful of series, and you're going to have to determine if they converge conditionally, absolutely, or diverge. And you're going to have to justify all of your arguments. You're going to have to cite all the theorems. I'll give you a theorem sheet, so you don't need to have the theorems memorized, but you will have to be able to use them appropriately. If you've got more questions, I'm always happy to answer them. Just know that that is going to be the test. I'm going to give you a bunch of series. Tell me if they converge or diverge. How do they converge, if they converge, and justify everything. All right. Okay. Thanks again for listening. I'm glad this one was super short, and I will see you all next time.